We're jumping right into the lecture. So where we left off last lecture was adding impedance sheets. So we're going to derive the integral equation now that describes the, okay, so what did we do last lecture? What we did was we used the boundary condition for perfect electric conductor to construct integral equation, right? We started with an expression for the scattered electric field in terms of the convolution of the surface current and the Green's function. And we knew what the incident field was, but the integrand contained the unknown current density. And the left-hand side of the equation, which was the scattered field plus the incident field, was also unknown because we don't know the scattered field if we don't know the current density, right? But we do know places in space where the total field, we do know what the total field is in certain places in space, right? For PEC, we know that the tangential electric field has to be equal to 0. And therefore, we can say the left-hand side is equal to 0 when we observe the scattered field plus the incident field, the total field on perfect electric conductors. Then we were able to solve the integral equation because the only unknown was the current density on the integrand, right? Here we're going to do the same thing, but we're going to use a boundary condition that's different from the PEC boundary condition where the total tangential electric field has to go to 0. Instead, we're going to use this impedance boundary condition where the total tangential electric field is equal to eta sheet times J. All right? So the same thing otherwise. We start with E total. We write E total as E incident plus E scattered. And we set that equal to eta S times JS, right? Where eta S is the sheet impedance of the homogenized metasurface, if you want, or the boundary condition, right? That's a sheet impedance. All right? So we can move the scatter field to the other side. So we have E incident equal to eta sheet J minus E scattered. And that is equal to eta sheet J plus J omega mu times the integral of J into G. So we express the scatter field in terms of the convolution of the current density with the Green's function. We know what the Green's function is in 2 dimensions. It's H naught 2. And for TE incidence, we know everything is Z polarized, right? The current is Z directed, the incident field is Z directed, and we get an integral equation here for TE incidence. For TM incidence, we have a similar integral equation, except the Green's function is not H naught 2 directly. It's the second derivative of H naught 2 with respect to X for these X-directed impedance sheets, and 1 over K naught squared plus 1, right? Okay, so we went over this last time. So the impedance sheet here, since we're using this H naught 2, the impedance sheet here is invariant in and out of the board. So we have the Y direction here, the X direction here. This entire strip here carries a sheet impedance of eta S. It's invariant in and out of the board. And therefore, the in and out of the board wave number Kz is equal to 0. And it's an infinitely thin sheet, right? So the boundary condition for this sheet is E tangential is equal to eta sheet times J. All right? Okay. So we do the same thing. Method of moment solution. EZ incident on the left-hand side is equal to E total, eta sheet times J, plus E scattered, or minus E scattered rather, which is given by this expression, right? We discretize the geometry, which in this case is an infinite impedance sheet in and out of the board, but finite width in the plane of the board, into pulse basis functions, where each of the pulse basis functions have a coordinate at their center given by xn equal to minus w over 2, puts you on this end of the impedance sheet. On the left end, we add half of a unit cell to get to the center of it, and then we move by integer numbers of unit cells to get to the centers of the remaining unit cells until we get to plus w over 2. And there are n of these. We expand the current density, the unknown current density in the integrand, in terms of pulse basis functions with unknown complex coefficients. Each of these pulse basis functions are non-zero only over their domain, which is a subdomain of the entire impedance strip, and of width delta, right? So they're equal to 1 over this domain and 0 elsewhere. All right, we substitute that expansion back into the integral equation. We can factor out the unknown coefficients in the summation sign, and we end up with an integral that we can solve, plus these other terms. So we have EZ incident, we have EZ total here. We've expanded the current JS in the total field term. We factored out the complex coefficients of the expansion functions for the current density, and we have left over a integral we can solve. We have to integrate the Hankel function again, right? So it's exactly like the PEC case, except now we have this extra term, which is eta sheet times j, right? And we have to expand that j as well. So these pulse basis functions here are non-zero only over the domain of the pulse, right? So this one, for example, is only non-zero over the nth pulse. Say the first one, for example. All right? Okay. Okay, so we use point matching now in order to generate n equations so we can solve for our n unknowns. And we therefore integrate both sides against the delta function centered at the center of each of the pulse basis functions. In other words, we evaluate the integrand at the center of each pulse. So we have EZ incident evaluated at xm, the nth observation point, is equal to eta sheet times xm times delta mn. Why do you think this delta function? Okay, so not delta function, but this is a operator delta mn that is equal to 1 when m is not equal to n and is equal to 0 when m equals to n. It is point matching, right?
Weighting function will be
Yeah, so this term right here, you can think of this term as the integral of delta of x minus xm multiplied by the summation, I suppose, of n equals to 0 to n minus 1 of I n times p n of x, right? dx. And then there's an eta sheet out front. All right? So we could pull the summation out. We get eta sheet times the summation of n equals to 0 to n minus 1. We have the integration of delta x minus xm. And we have, okay, so we could pull out the in's as well. And we end up with pn of x here. dx, right? All right, so what happens here? So only when this, so we're integrating here from, let's say, xm to xm plus 1, right? So only, so p of n, pn here, is only non-zero in its own domain. And this testing function is also non-zero only in its domain. So only when these two domains overlap will this give you a non-zero result, right? So, okay, so let's look at it like this. If I have a strip like this, if this is the Pn, right? So let's say this is Pn, then the delta function, so let's say this is 1, 2, 3, 4, 5, 6, 7, right? x7, and this is, say the testing function is here, right? So even though we're using delta functions here as our testing functions, if we do this integration, it's only over this domain, right? Because it's xn to xm plus 1. So since it's only over that domain, the Pn of x makes it 0, right? So only when xm to xm plus 1 is in the same cell as Pn of x do we get a non-zero result. Or m has to equal to n, right?
That's n for non-zero results.
Yes.
So then why is the delta reverse where it was?
Oh, this is backward. I'm sorry. Yeah, good point. Wrote that too fast. So this is when m equals to n, m not equal to n. Yeah? All right. Good. Okay. So now we can define a matrix equation from this. This is for all m's, right? M equal to 1, 2, 3, dot, dot, to n. So we can make a voltage vector from the left-hand side from samples of EZ incident, right? We're going to sample EZ incident at the centers of each of these unit cells, right? So we construct, when you sample EZ incident at this point, you're just going to get a single number. And you can arrange those numbers in an m by 1 vector, which is called V. All right, then Z sheet here is a matrix, which is a diagonal matrix due to this. It's only non-zero when m is equal to n, or when the row is equal to the column in the matrix. And we sample eta sheet at the center of each cell as well, right? Okay, and then ZMN is the impedance matrix, and we sample that, or we calculate that using this following expression, right? We integrate from xn minus delta over 2 to xn plus delta over 2, and we observe at the center of each cell, at the nth cell. Right? So you'll get a full dense matrix from this, ZMN. All right, so we solved the matrix equation for the unknown coefficients now by writing this as VM. So this is VM here is equal to Z sheet times IN. IN comes from this part. And then ZMN multiplied by IN, right? All right, that's this expression here. You can factor out the common IN, and you end up with this expression. Then you can invert the impedance matrix, Z sheet plus ZMN, and you can calculate the unknown coefficients of the expansion of the current density using this following expression. All right? The problem is we need to know Z sheet. So if you have a known sheet impedance, if you know the sheet impedance as a function of X along your geometry or the infinitely thin impedance sheet, then you can calculate the current density using this matrix equation. All right? Okay, for the TM case, you can do the same thing, and you get this as an impedance matrix. All other matrices are the same. All right? Good. So how did we get here? We have H02 and H22. And that comes from, remember we had to differentiate. So let's go back to the integral equation here. We have to differentiate the H02 with respect to X twice. And if you use the formula for the derivative of Hankel or Bessel functions, then you can express that as H02 plus H22. All right? Very good. All right, so now we can calculate the self terms. This is the same as we did before, except now we have a TM case, which we didn't cover previously. The TM case has this expression for the impedance matrix, which is the integration of H02 plus H22. We do the same thing. Since we want the argument of these Hankel functions to go to 0, we're going to express each of them using their small argument expansion. H02 is equal to 1 minus J2 over pi times the natural log of gamma k naught rho over 2. And H22 is very similar, except the first term is actually it's very different, right? So 1/2 k naught rho over 2 squared plus J1 over pi into 2 over k naught rho whole squared, all right? All right, so these are the small argument expansions for H02 and H22. The self terms can be evaluated then to be the following. So you just integrate. You substitute these in for these two terms and you integrate. All right, but you're integrating these that have absolute values, and you're integrating over one period. But because it's a self term, it doesn't matter which period that is. So you can pick any limits you want as long as they have a width of delta. So generally you can just do minus delta over 2 to delta over 2. Or you could do 0 to delta, whichever you choose. And as long as the discretization is uniform, then that same calculation can be used for all of the elements along the diagonal. And to deal with these absolute values, you have to split the integral into two terms, right? One up until one where the absolute value is positive, and then you have to swap the two terms in the absolute value and calculate the second half of the interval, right? Okay. All right. So once we have calculated the currents by solving the matrix equation, we can calculate the far field. The far field is found following the expression shown on this slide. EZ scattered is minus J omega mu or eta k. We integrate across the entire length of the impedance sheet, and we convolve the current density with the Green's function. And this is the Green's function here for the two-dimensional problem for TE incidence. And here's the Green's function for two-dimensional problem for TM incidence. We still have to differentiate it outside, right? We'll derive these later in the course. And in the last chapter, we're going to do Green's functions. Okay, and in this case, since it's TM polarization, the electric field is in the plane of the board, and that means you'll get a phi component in the far field. This TE incidence has the electric field in and out of the board, therefore you'll get a component, the Z component in the far field, right? Okay. The far fields then can be calculated by employing the large argument approximation for the Hankel function. Since we're going to take the observation point to infinity, the arguments of these Hankel functions go to infinity, and therefore we can substitute in the large argument expansion for the Hankel functions. And we can use the approximations for rho minus rho prime as rho minus x prime cosine phi. These are nothing but the parallel ray approximation for the far fields. And for the amplitude, we just use rho, right? Okay, so substituting in the large argument expansions, we can find the far field for the TE case and for the TM case using the following two expressions, right? Okay, so you'll need all these when you program when you do your homework, when you write your own moment method codes. Here is some code. So I don't know why the PowerPoint app on the iPad always expands my fonts like this. They fit nicely in the PDFs that you have online, but when I project them here, the font grows, I guess. So anyway, here's a program that calculates the scattering from an impedance sheet. All right, what do we do first? We define a couple of parameters. First parameter is epsilon naught. The next one is mu naught, and then eta naught. We set the frequency to 10 gigahertz. We write the speed of light, allowing us to calculate lambda, which is c over f. Then we calculate k naught, which is 2 pi over lambda. You'll probably start all of your programs with these first few calculations, right? Then we set the width of the strip to 5 lambda. We set the azimuthal angle of incidence. This is a 2D problem, so we have x here. We have y here. So there's a plane wave that's illuminating this thing with its, this is a TE case, I believe. So TE means that the electric field is in and out of the board, and this is incident at some angle with respect to the x-axis because this is a two-dimensional problem, right? So phi is our azimuthal variable that's in the plane of the board, and therefore this plane wave, which is illuminating this impedance sheet, which has width W in this direction and carries a sheet impedance of eta sheet as a function of x, is being illuminated by, right? We're calculating the scatter field due to this impedance sheet. All right, so the width of it is 5 lambda. We need this Euler's constant for our self terms. We set the discretization here. We're kind of overkilling it with 500 points, but because it's numerically efficient, you can do that. And then delta, then we calculate as the width of each unit cell, delta, right? Which is W divided by N, where W is the width of the sheet and N is the number of unit cells. M then is going to be, because we have two indices, M and N, right? M is going to go from 0 to N minus 1 from these summations, right? Let's see if we can find those, maybe here. Here. Yeah, so we're going to, M goes from 0, 1, 2, dot, 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 N minus 1, right? Okay, so 0 to M minus 1. Then we have the coordinates of the centers. We start at minus W over 2. We add half of a unit cell with delta. And then this index M increases from 0 to N minus 1 to give us the centers of each of the unit cells, right? Okay. And then N is equal to M. We have the same discretization for the basis functions as we do with the testing functions, right? So N is equal to M, and you can calculate Xn directly. So we define the sheet impedance here, eta sheet, as minus J100 ohms per square, if you want to write it like that, but minus J100 ohms. And then we calculate the voltage vector, Vm, which is just samples at the centers of the unit cells based on point matching. So Vm is equal to e to the jkx cosine of phi. Phi is this azimuthal angle of incidence. Phi equal to pi over 2 means what? What kind of incidence? Oblique or normal, or normal incidence, right? So we have normal incidence, and because we're coming in at 90 degrees, what do we expect this vector to be then? What? All ones, right? If the electric field is coming in normally, then it's uniformly illuminating this thing, right? Okay. So we fill the impedance matrix now. We have a double loop here. We start for M equal to 1 to N, and then N equal to 1 to N to fill the entire matrix for rows and columns. We check if it's a self term. If M is not equal to N, then it's not a self-term. We can calculate the impedance matrix mnth element of it by evaluating that integrand. Here we're doing, instead of doing numerical integration here, we're going to do midpoint rule. So it's k naught eta delta over 4, which are the coefficients of the impedance matrix definition. Bessel function 0 to k naught absolute value of xm. So the mth here from this, the mth coordinate of xm, right? Mth value of xm. So the mth observation cell and the nth source cell, right? Okay. All right, very good. And we multiplied by delta here, and we evaluated this integrand at its center, right? So that's called midpoint rule. Okay, if it's m equal to n, then we use the formula for the self-term that we got analytically by expressing the Hankel function as its small argument expansion and calculating the results of that integral. All right? And we fill up the entire impedance matrix like that. Then we calculate the Z-sheet matrix we know is a diagonal matrix. And it has eta sheet across its entire diagonal because the impedance sheet is uniform. Yeah? Okay. Then we find the current coefficients by solving the matrix equation Vm equals to Zmn plus Z sheet into In, right? And you just invert this and throw it to the other side. And that's what this line is doing. Okay, you can calculate the scattered field by multiplying negative Z times I. That's one thing you can do. But that's the scattered field evaluated on the actual impedance sheet, right? Okay, now we plot the current. So here's figure 1. We plot xm. We normalize the x-axis to the wavelength so we can express the data in terms of wavelengths. And we plot absolute value of the scattered electric field, which is the scattered electric field. That's one plot, right? So this is bad code, right? I'm plotting the scattered electric field. This says surface current density. This should be electric field. Scattered field, right? Okay. Then we plot the angle of, this is the phase angle of the scattered field. So this is the phase of scattered field. And this is the amplitude. Okay. All right. Then we calculate the far field. And the far field pattern we calculate here. So we start another figure. We set the far field distance equal to 1. We can do that. We're going to normalize anyway. We have a vector of observation points from 0 to pi. So here's the impedance sheet. Here's x. Here's y. This angle, we're going to observe phi going from 0, which is this point, to pi, which is this point. So we're going to get the upper half space. All right? Okay, so we calculate the far field by looping through our observation points and adding. So we add up. Okay, so these lines of code here, there's a summation here. We add up the current on every unit cell over to each observation point. Here's observation point 1, right? Then we repeat, move the observation point, add up the scattered field to the far field from the entire impedance sheet to give you that contribution at that angle in the far field. Then you change far field observation point, and you do it again. All right? That's what this code is doing. Okay, and then we redo it for TM incidents. All right, I won't go through the details of that. And okay, so you can calculate the rest for TM incidents. So here is the results for TE incidents. We have a frequency of 10 gigahertz. Phi incident is 90 degrees. Polarized in and out of the board. For TE polarization, we have the impedance sheet of minus J100 ohms. We have the angle of phi incident indicated in this figure like that. The width of the impedance sheet is 5 lambda. This should not say current density. This is bad. I need to fix this. So these are actually plots of the electric field, right? The tangential electric, total electric field on the impedance sheet. So ignore this title here. and this. I'll fix this, all right? But here's the far field. So it's a uniform impedance sheet. We expect, and it's being uniformly illuminated, so we expect the far field to be collimated, right? And we get the nice sync function with a 13.4 dB side lobe and a 1 over x kind of decay to the side lobe structure. All right? Here's the same thing. Now this is current density. Yeah, I believe this is current density. I'll go back and fix this. But here is the pattern for the TM incidence. All right? So now the electric field is not in and out of the board. It's in the plane of the board. We're still illuminating it normally. Why do you think that the side lobes, the pattern here, increases at the ends, but here it goes to 0, right? Why do you think that is? What? So here is the other pattern, the TE incidence. And then here we have the TM incidence. Why do you think that the pattern goes to 0 in the TM case for the far out angles, like 0 and 90 degrees?
The influence of the tangent to the sheet.
So what do you think the current, what?
Current, surface current.
What about it?
I think for TE, we have a bigger surface current in the
Why is it bigger?
current. The bigger units is like it goes up. I don't know.
Okay, very good. So this is the reason, right? So if there's the impedance sheet, the current for TE polarization has these singularities at the end, right? It goes like this. But for TM polarization, the current is in this direction, right? In the x direction. And it runs out of room. There's no more conductor or impedance sheet for the current to flow on. So the current has to go to 0 at this end and this end. So the current looks like this, right? So the current goes to 0 on the ends of the impedance sheet in the TM case, but in the TE case, the current does not go to 0. It actually has that singularity, that strong singularity is for perfect electric conductor, right? For the impedance sheet, that's not necessarily the case. For the impedance sheet, you don't get such a strong singularity, but you do get, the current is not forced to go to 0, right? That's the difference. I need to go back and check these plots. First thing we do next lecture is to revisit these two slides and make sure I got these right. All right.
So for the E case, the current is flowing outside of the board.
For the TE, I have a feeling that
Because I don't.
these are backwards. Yeah, ignore the surface current plots for now. I have a feeling this is the TM. No, okay. Ignore these surface current plots. They don't look right to me. All right. We'll come back to these next lecture. But that's the reason why, right? Okay, good. All right. Question? Well, did you have a question?
Yeah, the current for the D mode, so the current is coming out of the board.
For the TE, yes, the current is in and out of the board, right? The electric field is in and out of the board in this case. So the electric field is in and out of the board. And there's nothing anisotropic about this impedance sheet. It's an isotropic impedance sheet. Free space is isotropic, so the polarization cannot be rotated. There's no new polarization generated here, no cross pole for this. So that means the induced surface current is going to be z-directed in and out of the board, and the reflected field, the scattered field, is also going to be z-directed in and out of the board for TE polarization. For TM polarization, the electric field's in the plane of the board, right? So the current is flowing. So in this case, the current is flowing in a direction where the geometry is infinite, right?
Yeah.
Why is it not working? Okay, the geometry is infinite in and out of the board, right? So the current is flowing in a direction that's infinite. There's never really any discontinuity in the direction of the current. But in this case, the current is flowing in the direction where the dimensions are finite. Okay. Okay, very good. All right, so what was the problem before? We needed to know what the impedance sheet was in order to solve the integral equation, right? We had that back here. So we needed to know Z sheet before we could solve the integral equation, right? But what if we want to design the impedance sheet to give us a particular scattered field? So we know the incident field, we know the illuminating field. We want to design an impedance sheet to give us a particular scattered field. And the way we do that is described in the next part of this. So rather than solving the integral equation for a known sheet impedance, we can solve for a sheet impedance given a desired total field, tangential to the metasurface, right, or the impedance sheet. So we still use the same equality, right? We have two equalities in this expression. We have E total, from the boundary condition, we have E total equal to A to sheet J, right? So we have E total equal to E incident plus E scattered, and we know that E total itself is equal to A to sheet times J. There are two equalities in this expression, this one and this one. If we want to design the impedance sheet, then we use the left equality because we know what E total is, all right? If we want to analyze an impedance sheet with known impedance, then we use the right equality because we know what A to sheet is, right? Okay, so let's now derive the integral equation, assuming we don't know what A to sheet is yet, okay? So we do the same thing. We have E incident equal to E total. This is what we had before. The rightmost equality where we know A to sheet. We express the total field using the A to sheet times JS. Here's the total field. And then we have the current density expanded in terms of Pohl's basis functions and then tested using delta functions or point matching. And then we have the scatter field term like this, right? All right. If we're using the leftmost equality, which is for design, then we have E incident equal to E total. So we move, so from this expression, what we do is we move the scatter field to the other side. So we have E incident equal to E total minus E scattered. E scattered doesn't change, it's the same thing. But now we have E total. And because E total is known, remember E total is equal to E incident. We know E incident. It's the illuminating or the impinging electromagnetic wave. And we know, or we want to stipulate E scattered, right? So we desire a particular scattered field from this impedance sheet. All right. Well, if we add these two together by stipulating this and knowing this, then we know E total. We can then integrate over, xm to xm plus 1, delta of x minus xm into E total as a function of x dx. And this just gives you E total at xm, right? Which is this expression. We treat it the same as we do with the incident field. All right, good. So it's that easy. Now we can solve for the currents. We'll do that next. So now we have easy total here instead of A to sheet times J. We define a new matrix. So the V matrix is the same as before, but now we define a W matrix, which is, in the case of point matching, samples of the total field. And then we have the impedance matrix still. So the matrix equation becomes E incident equal to E total minus E scattered. And we can move this term to the other side now. And we can solve for the current coefficients in the following way. ZMN inverse into VM minus WM, right? Okay, good. So if you have a metasurface represented by a homogenized current sheet, or in our case, just an impedance sheet. Okay, so forget about this. This is the design approach, the steps in order to design it. We stipulate the desired scattered field. What do we want this impedance sheet to give us as a scattered field or a reflected field? We form the total field as the desired scattered field plus the incident field. Then we solve the integral equation to obtain IN. Then we go back to the boundary condition, which was, remember, E total equals to A to sheet times JS, right? Now we solve for the currents. And we stipulated E total. So the only thing left unknown is the sheet impedances. So now we just divide these two. So this is kind of poor notation. We have vectors. What is the derivative, or sorry, what is the quotient of two vectors? That's not really well defined. So this means element-wise division in this case. Yes.
That electric field is a vector like having XYZ component, and surface current density might have XY component, and so how the surface impedance can be expressed as scalar. I mean,
Yeah, very good. So in this case, we're talking about two-dimensional geometry, which means that it's invariant in and out of the board, right? It's infinite in one dimension, in this case, in and out of the board. And we're talking about isotropic problems here, meaning that for the TE case, we have only one electric field component in and out of the board and one current density in and out of the board. And the scattered field is also in and out of the board, the one we stipulate. So this will just be easy total divided by JZ on the surface, right? So that's a scalar value, as long as we're not trying to. So eta sheet equals to EZ total divided by JZ on the surface, right? In the case of TM, so, gosh, this is TE. For TM, we would have EZ total, no, sorry. Not Z. EX total divided by JX, right? Which is also scalar. It's because of the way we set up the problem, right? We're assuming that there's their isotropic impedance sheet. Okay, good question. So the total field samples are WM. We have that matrix already. And we calculate IM from here, and we can divide these two matrices element-wise, and we can get the sheet impedance for each of the unit cells. All right, very good. All right. So we can add ground planes and dielectric layers now. Okay, well, first we're going to add ground planes. So we talked about the impedance sheet first, right? So we have sort of a meta surface, which is represented by a homogenized impedance sheet. And we're going to place that, oh my God, every time my palm touches this thing. So we're going to place that at a distance D above a perfectly conducting ground plane here, PEC. So here we have, this one is an impedance sheet. And this one is a PEC plane. All right.
And you're just stacked on top of each
Yeah, they're placed, there's an air between the two. They're placed a distance D. So the impedance sheet is placed a distance D above the PEC ground plane. The width of the ground plane here is W ground plane. And the width of the impedance sheet is W. We're going to expand the current density in terms of pulse basis functions again. And we're going to use point matching again. But now what we're going to do is construct 4 total matrices. All right. So there are 2 separate currents. There's the current on the metasurface layer. There's the current on the ground plane layer. All right. And we're gonna construct 4 matrices. I'll show you what those are. But the field that you observe on any given unit cell in the metasurface layer, for example, on the impedance sheet here, for example, what is the total field that we observe there? It's due to this current, the self current, this cell, that cell, and so forth, right? Dot, 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 all of these, but also due to the current on the ground plane. So this current radiates to that cell, this current, all the other currents. So you have to add up the contribution due to the pulse basis functions on the layer 1 and those on layer 2 as well. All right? Okay, so how can we express that in terms of the integral equation? We have EZ incident XM1. 1 means layer 1. So we're observing at the empty cell in layer 1, here for example, is equal to EZ total in that cell, plus the summation, plus the scattered field, or minus the scattered field rather, due to the currents on the layer 1, the metasurface layer, plus the scattered field due to the currents, or sorry, minus, due to the scattered field due to the currents on the ground plane layer. All right? So the Green's function now, instead of being absolute value of x minus x prime, is going to be h naught 2 k naught times rho minus rho prime, right? If everything is x, like before when we only had an impedance sheet, you could express this as absolute value of x minus x prime, right? But now, because rho is a two-dimensional vector, it could be, here's the origin of the coordinate system. So it could be down here. It could have an x and a y components, right? If this is rho prime, for example. So that means that rho minus rho prime is equal to the square root of x minus x prime squared plus y minus y prime squared, right? Okay, so that's what you see here. But this is the scatter field. The first term here is the scatter field due to the currents on the metasurface layer or the impedance sheet. And we know that x prime here has a y coordinate of 0, right? And the ground plane layer has a y coordinate of minus d, but it's minus y prime, y minus y prime. Y prime is minus d, so you get y plus d, right? Okay. So this is the same as we had before, this entire part here. But now we've added an additional term, additional scatter field term. The scatter field coming from the currents on the ground plane. All right? Okay. Okay, so now we can convert all of these integral equations into matrix form, right? And we get Vm1 observed on the impedance sheet layer is equal to the total field observed on the impedance sheet layer plus Zmn into I1 observed on the due to the scatter field due to the impedance sheet layer, and plus Z12 Mn times In2, where In2 is the currents on the ground plane layer, and this matrix is this impedance matrix here, which links the scattered field observed on layer 1 due to the currents on layer 2. Yeah? Is it clear? Any questions? Yeah.
Explain WM.
Yeah. So WM is the samples of the total field, right? So before we had E incident equal to A to sheet J. If we go back here, either we use this equality where we know E incident plus E scattered is A to sheet times J when we have an analysis problem, when we know A to sheet. If we don't know A to sheet, we use the left equality and we define what E total is, tangential to the metasurface, right?
I'm just about the 1 and 2. So are you?
Oh, okay, good. So there's 2 layers now, right? So anything that has subscript 1 means layer 1, the impedance sheet. Anything that has subscript 2 means layer 2, the ground plane. So if you look here, this impedance sheet, okay, hold on, I can't get this thing. Oh, here we go. So Z11 is the observation on layer 1 due to the currents on layer 1. Z12 is the observation on layer 1 due to the currents on layer 2. WM1 is the total field on layer 1.
So you can take set samples of the fields on both layers you're solving.
Well, okay.
So like if you were trying to find the impedance.
What is the total field? What do you think WM2 is?
Is that on the PVC?
Yeah. Zeros, right? So we define WM1 and WM2. So this is for observations made on layer 1. We also have to construct an integral equation for observations made on the ground plane for each layer, right? So here we have the same integral equation or similar one for observations made on the ground plane layer. We have EZ incident at XM2, which are the points of observation on layer 2, the ground plane, the total field on layer 2, the scattered field observed on layer 2 due to the currents on layer 1. So we have observations now on YM2, but source at y equal to 0. And the scattered field observed on layer 2 to the currents on layer 2. So we have YN2 and D. So then we have this matrix equation. VM2 is equal to WM2 plus ZMN21 IN1 plus Z22 IN2, right? Okay, you can probably see where we're going with this. we are going to combine these two matrix equations into one big matrix equation using these as blocks, block matrices. So we can combine these two, VM1 and VM2. VM1 is the incident field observed on layer 1. VM2 is the incident field observed on layer 2. We have WM1 and WM2. Then we have Z11, Z12, Z21, and Z22 multiplied by the currents IN1 and IN2 as a vector. All right? Is this clear? Everybody understand it? Very good. Very nice. All right. Well, now you can invert. Everything is known here, right? We stipulate what the total field is on layer 1 because the far fields or the scattered fields. So if we treat layer 1 as the aperture, right? Treat this as the aperture of the two-layer system, then the far field will be related to the near field that you calculate or the total electric field on this layer. Is that clear? I don't know if you guys taken an antenna theory course, but the far field is the Fourier transform of the near field, and the near field in particular, the near field in the aperture of the antenna. And the aperture can be considered, in this case, the first layer, the impedance sheet layer. All right? Okay, so we stipulate E scattered on this layer, desired. All right? On this layer, we don't need to define E scattered. All right? The desired scatter field, rather. Matter of fact, you don't need to do that anyway because we know what the total electric field is on that layer anyhow. It's 0, right? Because it's a PEC layer.
So the scatter field will be the near field from the ground plane?
No, the scatter field is due to the currents on both the layers, right? But you can consider the aperture. Okay, so the aperture of an antenna like this, right? Say the aperture is just above both layers. And we want to calculate what the electric field is here due to both layers, the currents on both layers. So we're going to add up the currents due to all of these, right? Dot, 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 and all of these, right? Now, if this aperture layer is infinitesimally above layer 1, this is the aperture, right? Definition. Well, if you move this aperture as close as you can to layer 1, then you can kind of treat the total field on layer 1 as the aperture. Because that's exactly what we're doing when we calculate what the total field is there, right? We take the incident field here. Oh my goodness. Take the incident field here, add the scattered field due to all the currents. That's exactly what we're doing, right? Okay. All right, very good. So we know all of these impedance matrices. We know WM1 and WM2, VM1 and VM2. We can calculate IN1 and IN2. Yeah? All right, good. Okay, so last semester we taught the volume equivalence principle. In order to add dielectrics in this 2D case, one approach is to use the volume equivalence principle and expand the polarization currents inside of the dielectric layer. So here we're going to go over a review of the volume equivalence principle because we're going to use it here to model the dielectric spacer. So assume in free space the sources Ji and Mi generate the fields E0 and H0. So we have free space, we have some sources. Oh my gosh, every time I put my palm on it. We have sources Ji and Mi in free space. They generate the fields E0 and H0. All right? These fields obviously satisfy Maxwell's equations. So curl of E0 has to equal to minus Mi minus j omega mu naught H0 because we're in free space, mu naught. And the curl of H0 is Ji plus j omega epsilon naught because we're in free space, E0. All right? That's one thing. The next thing is we have the same sources, Ji and Mi, but they radiate in a medium represented by epsilon and mu rather than epsilon naught and mu naught. They generate the fields E and H. So that makes sense. If I take two currents, J and M, and I put them right here in free space, then they will radiate E0 and H0, some field, right? If I change the entire universe to epsilon mu rather than epsilon naught mu naught, and I put those same two currents in space at the same points, then they'll radiate a different electric and magnetic field, right? E and H. Subtract the two and define the scattered field as E scattered equal to E minus E naught, and H scattered equal to H minus H naught. All right, so that's the key. So we take these two equalities, right? Since these are, we're allowed to take two equalities and subtract them, and we don't disrupt the equality, right? If I take A equal to B and C equal to D and I subtract those two equalities, and I still have a new equality that's also an equality, right? Okay, so I subtract the two results. What do I get? I get the curl of E minus E naught is equal to minus Mi minus negative Mi, which is plus Mi. Then we have minus j omega mu H. Oh, hold on a second. Let me not make that a H minus j omega mu naught H. All right. Okay, you can factor out the H. You get this expression here. And we're going to define the scattered field as E minus E naught, right? It's okay, why is it defined that way? The electric field, the scattered field is defined as the field due to the presence of the object, right? The perturbation due to the perturbation to the incident field due to the presence of the object, right? Incident field is omnipresent, it exists everywhere. The scattered field is due to the placement of that object in the incident field. So E scattered can be defined as E minus E naught, and H scattered in a similar way. So we have curl of E scattered is minus j omega mu minus mu naught into H minus j omega mu naught H scattered. All right? There's something wrong here. This should be H, and then this should be H naught. Let me see what we did here. So the curl of E scattered minus j omega mu H minus mu naught H. That makes sense. And then we have minus j omega mu naught H scattered. Okay. All right, so let's see if we can do this derivation really quick. So the left-hand side, oh, I see. So I think what we're doing here is we're taking curl of. So here we have we have the curl of E minus the curl of E naught, right? From this part. And we're going to keep E minus E naught is E scattered. That makes sense. And then on the right-hand side, we have minus j omega mu minus mu naught. That makes sense into H. Oh, but then we got to express H naught here, this H naught, in terms of H. So that means we have minus j omega mu naught, and then H naught is H scattered minus H, right? H scattered minus, no, it's the other way around. So this is minus, this is plus. Yeah? Okay. So then we have a minus j omega mu naught H scattered, this term here. All right, good. So if we look at this, what we'll notice is that this is a Maxwell equation for the scattered field, right? Same with this one. This is the other pair. We have the other Maxwell equation for the scattered field, which is the quantity of interest. But it has this additional term here. If we can make this into a current, then we would have exactly the Maxwell equations, right? So these terms can be thought of as the sources that give rise to the scattered fields. Therefore, we can define a new current, an equivalent current, as M equivalent is equal to j omega mu minus mu naught into H. The scatter field can be thought of as generated by M equivalent. Same thing here. We can define an electric equivalent current density as j omega epsilon minus epsilon naught into E total. And we can think of the scatter field as generated by J equivalent, right? Okay, this doesn't help us very much. We do have equations we can solve, a pair of Maxwell equations for the scatter fields, E and H scattered. Although we need to know E and H total already, right? Which kind of doesn't help us, but we might be able to define those in this slide. So what do we have here? We have these two these two differential equations, Maxwell equations here. The curl of E scattered is minus M equivalent minus J omega mu H. We have the curl of H scattered is J equivalent plus J omega epsilon naught E scattered, right? We have an incident field. We have a dielectric object of epsilon r mu r, and it's placed in free space. And we illuminate this with an incident field, and there's a scattered field. The scattered field is described by these Maxwell equations here. Okay, if we use these equivalent currents here, then these equivalent currents can be placed in free space. Right? These are free space Maxwell equations. Right? So we can place these equivalent current densities, J equivalent and M equivalent, in free space, suspended in free space, and we can calculate the scatter field due to them. So everywhere is free space now. So that's the whole, that's the benefit of using this volume equivalence principle, right? We can remove the dielectric object, and we can place equivalent currents suspended in free space that radiate the scattered electric field. And why is that useful? Because now we can use the free space Green's function to calculate the scattered electric field, right? Okay, let's take a look at the equivalent currents here. For sheet impedances, we had the boundary condition of E tangential equal to eta sheet times Js. Yes.
Those equivalent currents, how are they distributed in the space where the dielectric was? Is it like are they volume currents or?
Oh yeah, this in general, they're volumetric currents, right? Their J equivalent is a vector, and it's a function of x, y, and z. And a vector field, and it's a function of x, y, and z. So they're distributed throughout. There'll be zero outside of the original dielectric, the support of the original dielectric, but they're non-zero inside. So we've replaced this dielectric object with a bunch of current in free space, right? Okay. So the sheet impedance boundary condition that we've looked at is E total equal to eta sheet times J. Let's look at this equivalent current density. Here's the equivalent current density. It looks very similar. J is equal to something multiplied by E total. So if we divide both sides by this part, then we get E total is equal to something multiplied by J equivalent. And we can call this something here a volumetric impedance, eta V. So eta V multiplied by J equivalent gives us E total. All right? Okay, good. And we can calculate what eta V is, right? We specify the dielectric permittivity, epsilon. We know epsilon naught, we know the operating frequency, therefore we know eta V. All right, good. So for dielectric spacers, we have this kind of boundary condition, or this is not really a boundary condition. It's not a boundary, it's a volume, right? So this expression, this relation, E total equal to eta V times J equivalent. All right. Okay, so to add a dielectric layer now, say we have layer 1 here, which is the impedance sheet layer, then we have a ground plane layer down here, normally. But here we're going to discuss only the dielectric layer. We're going to, the volume, or the discretization, the expansion of the polarization currents in this case are not surface currents that are existent on an infinitely thin layer, like the impedance sheet and the ground plane. Now we have volumetric polarization currents, and these volumetric currents have to be discretized in terms of basis functions which span an area in this case, because we're still talking about a two-dimensional problem with invariance in and out of the board. So we discretize this now into cells which have a delta X and a delta Y. All right? So they look like this. Instead of pulses that are, like this, where this is delta wide and this is just, in the X direction only. And then we have, so they look like this, right? So here's X, then here's a pulse, and this is the height of the pulse. So let's say Pn of X, right? And this is always equal to 1. Instead of being one-dimensional like that, they're now two-dimensional. They have a delta X and a delta Y and the unit height or unit amplitude in the vertical direction. But the vertical direction just represents the amplitude of the pulse basis function, right? So these are all amplitude equal to 1. Their heights are equal to 1 to start off with, right? Then we solve for the current coefficients, and each of these these cubes, will be scaled in height. They become rectangular prisms, and you get the approximation, the piecewise constant approximation of the polarization current in the dielectric layer. Yeah? All right, so now when we expand this volumetric current in the dielectric layer, it's a function of x prime and y prime because it has thickness in the y direction. We still express it in terms of pulse basis functions, except now these pulses are two-dimensional pulses. They have one complex coefficient per pulse basis function, and there's n sub v of them. All right? And this pulse basis function now is equal to 1 if x minus x prime is less than delta x over 2 and y minus y prime is less than delta y over 2. All right? And it's 0 otherwise. Is it clear? Yeah? Well, that's amazing then. All right. You'll when you go into it in your homework and start to write the code and all that is when you'll start to have more questions. All right. So here's a metasurface that has a line source inside of a dielectric layer. We have a ground plane, a dielectric spacer, and an impedance sheet, which representing this pattern metallic cladding on top, right? These printed circuits will be homogenized and represented as an impedance sheet. All right. Okay. All right. So now what do we have? We have an additional layer. There's layer 1, which is the pattern. Okay, imagine this is an impedance sheet, because that's how it will be represented in the integral equation. There's a process called homogenization where you can take printed circuits that are sub-wavelength like that, and you can average them over their unit cells and represent them as an impedance sheet. So this pattern metallic cladding on the uppermost layer of printed circuits, just think of it as an impedance sheet in the end. All right? So this is layer 1. Then we have the dielectric spacer, which is layer 2, and the ground plane, which is now layer 3. All right? So in the dielectric spacer layer 2, the incident dielectric field now is observed as a function of x and y. So we're talking about an xy coordinate or an xy position of a particular observation point in the dielectric layer. So this integral equation is going to be constructed around observations made in layer 2, in the dielectric layer. So now it's a function of x and y, easy incident. We have a to v multiplied by in2, the currents in layer 2. This is nothing but E total in that layer. Then we have in1, right, multiplied by the impedance matrix, or the scattered field observed in layer 2 due to the currents on layer 1. So you'll see the source coordinates. The source coordinates here are y equal to 0. And the observation are xm2, ym2, right? The observation coordinates. All right. Then you have the integration or the electric field observed in layer 2, the scattered electric field observed in layer 2 due to the currents in layer 2. So the currents in layer 2 are two-dimensional. So you have to integrate over x prime and y prime now. So you get a double integral here, right? And you integrate over delta x and delta y, right? Or a unit cell of width delta x and height delta y. And we have to integrate against x prime and y prime. And the observations are some point matching in the dielectric layer with coordinates x m2 and y m2. Yeah? And then you also have the contribution due to the ground plane layer. So these are currents that are source coordinates at z or y equal to minus d. And then you're observing in the dielectric layer at xm2, ym2. So now there's three scatter field terms, right? Well, so it's the ground plane is located at y equal to minus d. Because the y equals to 0 is at the metasurface plane. So the coordinates like this, y and x. And if you look at it in the cross section like this, the ground plane, this is the impedance sheet, this is the y-axis, this is the x-axis, and this thickness here is d. Yeah?
But if y prime is minus 2, we wouldn't have a plus.
Should be y2 minus, so it's y minus y prime. Yeah, this should be a plus. Good. Yeah, that's right. That is correct. Good. Good catch. All right, good.
Well, the y and 2 will be always the same, right?
The y and which one?
In the third layer.
Okay, the ground plane layer, right? So this has currents in2 This is the total field, IN2, observed in layer 2. This is the current coefficients in layer 1, the current coefficients in layer 2, and the current coefficients in layer 3, right? So they're all different. Yeah?
The coordinate is ym2.
Yeah. So this is the mth observation point, the mth observation point in the dielectric layer. So let's go back here. So here's X and here's Y, right? All right, let's say this point here, the center, point matching at the center of the cell, is going to have coordinates. Okay, so this point might be, let me see how I can. This point has coordinates x12 and y12, right? Where x12 is going to be, so you have to discretize this thing. You can discretize it any way you want. The way I've done it here is I've started with cell equal to 1 here, gone to 20, and then loop back to the next row and gone to 40, right? So the whole first row for the observation points will have the same y coordinate at y equal to minus delta divided by 2. So this will have, this is minus delta divided by 2, right? And the x coordinate's going to be, 1.5 times, oh, this is delta y, right? Delta x. Yeah? Okay. All right. That's the hardest part. You got to do all the bookkeeping of all the cells and define all your coordinates and then integrate over them and so forth, right? Okay, good. So now all we have to do is combine all the integral equations. So we have layer 1 and layer 3 we studied when we added the ground plane and the impedance sheet, and then the dielectric layer became layer 2. So we have V1, V2, V3. We have W1, where we stipulate the total field on the metasurface layer, the impedance sheet layer. V2 is eta V here. So we don't define a total field for that. We leave it as eta V times J because we know what eta V is for a dielectric layer. So we can leave it in the impedance matrix. It's a known quantity. And then E total equal to 0 on the ground plane layer. So we can express it like that, right? And then we have Z11 is the impedance matrix which links the scattered electric field observed on layer 1 due to the currents on layer 1. And Z23, for example, is the scattered electric field on layer 2 or in the dielectric layer due to the currents on the ground plane or layer 3, right? Okay, so you calculate all of those and everything's known now. You can solve for these currents through matrix inversion. Then you can go back to find your sheet impedances on the metasurface layer or the impedance sheet layer by dividing E total by JS. This should be E total on layer 1, JS on layer 1. So it's explicitly defined here. Yeah? Is it clear? All right. Good. Very nice. So let me see if I have an example. No, we go into, oh, we have to calculate the self terms in the dielectric layer, right?
Can I have a short question?
Yes.
For dielectric layer, we subdivide in y direction. I mean, we have a lot of blocks to disperse in a y direction, right? Should I say?
Yeah. So
Do I understand correctly?
you have to subdivide this into unit cells now, or pulse basis functions which have two dimensions, x and y. So this is delta x versus delta y. And you have to break the dielectric layer, which in this case has thickness in the y direction. It's infinite in and out of the board, right? But in the two-dimensional electromagnetics problem, it has thickness in the y direction. So you have to discretize it in the x direction and in the y direction. But because these are generally thin in metasurfaces, it's like a RF substrate, then this is kind of an efficient way to do it. But if you try to do volumetric discretization in a three-dimensional, which we'll look at later, a three-dimensional scatterer, then volumetric meshing is not an efficient way to go. And
Two layers.
well, okay, so the resolution I have here in resolving the electric field in the dielectric layer has only 2 points in the y direction. This I just did so I can expand it so you can see it. You should probably add a variable in your code so you can add multiple rows, as many as you want. Probably 5 rows or whatever, right? Depending on how thick it is. So you have to add another row of, this is your resolution for your electric field. You're only going to get one value at each of the centers of each of these boxes. So if your problem is such that you predict that the electric field doesn't vary in the vertical direction very much, if it's super thin, then maybe you can get away with something like that, right? Any other questions? Yeah.
How would you know when you have an appropriate number of rows? Like when I guess when your results stop changing?
Exactly, yeah. So in commercial solvers, they look for field gradients where the field is varying fast, and they add more unknowns there. Adaptive meshing. You, as a programmer here, what you'll do is add more rows if the results don't change. That's a hard thing to do is convergence studies. So add another row, add 2 more until you're satisfied that nothing's changing, right? Yes.
For homogeneized current sheet, we have an expression as E equals eta J, right?
For the homogenized current. Okay, you mean here?
I wonder that not every point in electric field equals J eta, right?
Yeah, that's the approximation you're making. So you're averaging the electric field, which is inhomogeneous in a cell. You're averaging it to make it homogeneous.
So the average of electric field equals eta average of J, right?
Yes. This is an average boundary condition, homogenization. So the average electric field, the average total electric field is equal to eta sheet times the average current density, surface current density. Otherwise, eta sheet wouldn't be a constant, right?